let's take a look at another example. This is coming from section 2.4. Suppose we're asked to solve the following differential equation presented in differential form. The first thing we would want to do is to check to see whether or not the differential equation is exact. So our function m of x comma y, that is equal to the coefficient function for the dx. This is going to be equal to, we have e to the 2y minus y cosine of xy. And what we want to do is we want to take the derivative of m with respect to y. So we're looking at the partial of m with respect to y. So I'm going to differentiate this equation with respect to y. The derivative of e to the 2y is going to be 2e to the 2y, coming from the chain rule. And now be a little bit careful. Whenever we differentiate the second term, it's actually a product, so we're going to need to use the product rule. We're thinking of it as the function negative y times the cosine of xy. The derivative of y is negative 1. Leave the cosine of xy term alone. And now we have our minus y. We now need to multiply by the derivative of cosine xy. We know the derivative of cosine is negative sine. So we're going to get a negative sine of xy. And then from the chain rule, the derivative of the inside with respect to y would give us x. So the partial of m with respect to y, just clean it up a little bit, it's 2e to the 2y minus the cosine of xy, and then we're going to end up with a plus xy sine of xy. So that is our partial of m with respect to y. We now want to look at the function n. N of x comma y is the coefficient function for the dy term. So we have n of x comma y. This is equal to 2x e to the 2y minus x cosine of xy plus 2y. And what we would like to do is take the partial of n with respect to x. So partial of n with respect to x. For this first term, the derivative of that with respect to x would just be 2e to the 2y. For the next term, we're going to have to use the product rule again, thinking of this as the function negative x times cosine of xy. This would be the following. Derivative of negative x is negative 1 times cosine of xy. And now we have the negative x. We need to multiply by the derivative of cosine of xy. That's going to be negative sine xy. And then the derivative of the inside part with respect to x would be y. And then lastly, the derivative of 2y with respect to x, that would be 0. So we find that the partial of n with respect to x is 2e to the 2y minus the cosine of xy, and then this becomes a plus xy sine of xy. Quick inspection, we see that these two partial derivatives are indeed equal. So because the partial of m with respect to y is equal to the partial of n with respect to x, that means that we do indeed have an exact differential equation. So that proves exactness. Now that we know that we have a exact differential equation, we know that this came from the differential of some function. So in particular, we know that our component functions, m, we come back up here, m was the partial of f with respect to x. So we can rediscover f up to a constant by integrating m with respect to x, and that will allow us to get the function f back. We also know that n is the partial of f with respect to y. And alternatively, there's more than one way to do this. We could instead, if we choose to, we could integrate this n expression with respect to y, and that would give us the function f, but up to a constant function of x. So really we have some choices. It's not like we have to do it one way or another. In the last example I did, I integrated m with respect to x, and I'll do that again. But just be aware that if you wanted to, you could solve this exact differential equation by solving integrating n dy. So here's what we know. We know that f of x comma y, this should be equal to the antiderivative of the partial of f with respect to x dx. That is going to be equal to the integral of m. This is e to the 2y minus y cosine of xy. And we're going to be integrating this dx. With respect to x, e to the 2y is a constant. So that antiderivative is going to be e to the 2y times x. Negative y is a constant. So we can use constant multiple to just kind of leave that part alone. And now we need to find the antiderivative of cosine of xy dx. This is a basic u substitution. Let u be equal to xy. Du is going to be equal to y dx. And perhaps it would have been better, in retrospect, let's not take that y out. Let's leave this as it is. So I have the minus sign. Let's keep the y there, because we need the y dx to complete our u substitution. So this now becomes the cosine of u du, because everywhere we see an x times y, we can put u. That's inside the cosine function, and the y dx gives us our du. The antiderivative of the cosine of u is the sine of u, and then back substitution, that'll give us the sine of xy. So this is minus the sine of xy, and then recall, because we were doing the antiderivative with respect to x, that our constant of integration here is actually going to be some function of y. Let's call that g of y. We can now go ahead and solve for the function g of y. So here's where we're at right now. We have that f of x comma y is equal to e to the 2y times x minus sine of xy plus some function of y. If we now take and differentiate f with respect to y, so remember, a moment ago we just integrated it with respect to x. We're now going to differentiate it with respect to y, because we know that the partial of f with respect to y, if it was an exact differential, and we know it is, then that should be equal to n of x. So I'm going to differentiate this expression with respect to y. That's going to give us a 2e to the 2y x. Derivative of this using the chain rule with respect to y, you're going to end up getting a negative x cosine of xy, and then plus g prime of y. And this should be equal to n of xy, which is 2x e to the 2y minus x cosine of xy plus 2y. And now we have an equation where we can solve this for g prime of y. To get the g prime of y by itself, I would subtract this from both sides. That cancels. I would add that to both sides. That cancels. And what we see that we get is the following. G prime of y is going to be equal to 2y. So we can find g by simply integrating both sides. This is a simple antiderivative of a single variable, integrate both sides with respect to y, we get that g of y is going to be equal to y squared. I'll leave the constant off. I think in the last example I put the constant there, but we know that if you look at the right-hand side, whenever we were to integrate the right-hand side, the differential of a constant is equal to 0. So I'll save that for a moment. So now we know the function f entirely. The function f was e to the 2y x minus the sine of xy plus g of y, which we solved for explicitly. That's going to be y squared. And again, if you look at this original differential, we knew that the differential of f was 0, so that meant that that function f of x comma y must have been equal to a constant. And so that's our solution for this differential equation. We get x e to the 2y minus the sine of xy plus y squared plus c. Out of curiosity, I'm just going to go ahead and do this. So there's no reason to have to solve this again because we just found the solution. But let me just show you that it's equivalent if you instead kind of focus your attention on the n of x term and work off of that to find f. So I mentioned this a moment ago, but typically I try to be as consistent as possible. So I'll always integrate m with respect to x if it's exact to find my function f. But we know that n, when it's exact, was the partial derivative of some function f with respect to the y variable. So another way to find f of x comma y is alternatively we could have integrated that function n dy. That looks like a horrible looking w. Let me switch that up. N of x comma y. Let's try that and see what the work would look like if we follow that logic. This would be the antiderivative of 2x e to the 2y minus x cosine xy plus 2y, and now we're integrating dy. Okay. So I'm going to be a little bit brief with some of this work. But again, you're going to want to take the antiderivative of all of these functions with respect to y. The antiderivative of 2x e to the 2y, that would give us x e to the 2y. You would want to do a u sub with letting u be 2y, and that's what you would get. The antiderivative of negative x cosine xy with respect to y, that's going to end up being a negative sine of xy. And then antiderivative of 2y, well, the antiderivative of 2y would be y squared. But now because we're doing the integration with respect to y, we would have some function of x. I've already used g before. Let me just maybe call it, I don't know, h of x would be our function of integration. So this is what we get for f. So we almost essentially know f up to whatever this constant function of integration h of x is. So we have f of x comma y is equal to x e to the 2y minus the sine of xy plus y squared plus some function of integration with respect to x. Well, what we know is that we just integrated that previous expression. We integrated n with respect to y to get f. If we now take that and differentiate it with respect to x, then that should give us that function m of x comma y. So if I integrate with respect to y, now I'm going to differentiate with respect to x. The partial of f with respect to x is going to be equal to, this would give us an e to the 2y minus y cosine of xy. Derivative of y squared with respect to x is 0. We get plus h prime of x, and this is supposed to be equal to m of x comma y, which is this function right here. That is e to the 2y minus y cosine of xy. We can solve this for h prime. To get h prime by itself, we would subtract e to the 2y from both sides. We could add y cosine of xy to both sides. And what we would see is that h prime of x is equal to 0. We can integrate both sides with respect to x. And we simply get that h prime of x, the h of x is nothing more than a constant. Okay. So for our solution, here's what we come up with. We know we have x e to the 2y minus the sine of xy plus y squared plus h of x plus c. And this right-hand side was supposed to be some constant. I could subtract that other c over, so that essentially what we get is our solution is going to be x e to the 2y minus the sine of xy plus y squared equals a constant. And this is the exact same thing that we did and we came up with when we did it in the other direction. So it's up to you however you want to solve these. My advice is once you find one way you're content with and you can get efficient with, just stick to that. For me, I'm almost going to always do it like we did the first time around. We'll integrate m with respect to x.